A solid disk of mass m and radius r has a moment of inertia of 1/2 mr squared. A ring would have a moment of inertia of just mr squared. So let's write those in. Okay. They say, consider a situation where you've got a 20 centimeter diameter object and a mass of 0.96 for the ring. They give a disk mass as well. It's 1.87. They say the disk is initially rotating at 182 revolutions per minute, but the ring is not rotating. After the ring is dropped, friction causes the ring to accelerate until it's riding along with the disk. So it takes us through the calculations step by step. It's going to be a conservation of angular momentum problem. So first, let's find the moment of inertia of the disk. Alright, so that's going to be 1/2 mr squared. So that's 1/2 1.87 kilograms times 0.1 squared. I get 0.00935. Okay. Next, we want to calculate the moment of inertia of the ring. That's going to be mr squared. 0.96 kilograms, 0.1 meters squared, 0.0096 kilogram meters squared. Next, what is the angular momentum of the disk before the ring was dropped? So we're going to want to use that formula L equals I omega, because we know the moment of inertia of the disk, and they also gave us the disk's angular speed. Moment of inertia of the disk was 0.00935. And we have to multiply by the omega, but you don't want it in revolutions per minute. We got to get it into the SI units, standard units of radians per second. So let's do 2 pi radians per revolution. And we'll multiply by the fact that there's 60 seconds in a minute. That'll get it converted there. I believe I'm getting 0.178. Now they say, what's the rotational kinetic energy of the disk before the ring was dropped? So that has its own formula. Kinetic energy of a rotating object is going to be 1/2 I omega squared. Alright, so similar to the linear version of that formula. This is for the disk, so let's plug in his moment of inertia and his angular speed. So basically I gotta copy all of this, okay, because I need it converted. And not only that, but we have to square it. I think it's 1.698. It'll be joules for kinetic energy. It's energy of rotation now. Now they say after the ring is dropped, when the ring is rotating together with the disk, what should be the final angular momentum of the combined system? So we have to have conservation of angular momentum. So this angular momentum that the disk had initially is going to equal the final angular momentum of the whole system, because that's the only angular momentum that it had originally. So let's write those values in. Okay, now after the ring has dropped, when the ring is rotating together with the disk without slipping, the total moment of inertia of the entire system will be given by the inertia of the disk plus the inertia of the ring. What is the angular speed of the combined system when the ring is rotating together with the disk? So we can find that total moment of inertia. Going to add moment of inertia of the disk plus the moment of inertia of the ring. .0190. Now, in order to solve this one, we have to use the idea of conservation of angular momentum. So this means the sum of all angular momentum at the beginning has to equal the sum of all angular momentum at the end of the problem. So how much angular momentum did we have at the beginning? We had 0.178 kilogram meters squared per second. This was all due to the rotating disk. Now at the end, we're going to substitute in the formula for angular momentum, which is moment of inertia times omega. And we're going to figure that the ring and the disk are going to be combined into a moment of inertia of 0.190 kilogram meters squared at this time. So plug that in. And now we can solve for the final angular speed. It's 9.39 radians per second. And just for comparison, the initial speed in radians per second was 19.1. So the angular speed of the system slowed down once the ring was dropped onto the disk. One last question that's asked here is, after the ring has been dropped, when the ring is rotating together with the disk, what is the final rotational kinetic energy of the system? So for that, I'll use the formula K equals 1/2 I omega squared. Our new moment of inertia is 0.019 kilogram meters squared. And we now know the final angular speed. So we can get that final kinetic energy. It's 0.827 joules. Keep in mind the initial kinetic energy of the system was 1.698 joules, so there was a loss of kinetic energy in this interaction. But kinetic energy doesn't have to be conserved in all interactions here, just angular momentum does.